So the point is going to be the following. I want to define a measure, but I'm not going to do it immediately because as it turns out, you can't measure everything. Some sets are just too wild to measure. So the first thing you're going to do as a pre-processing step, is to define what are the measurable sets. After you're going to do, you're going to kind of distinguish some sets from all sets you might care about in a certain way. And only after doing that, we'll be able to put a measure on those measurable sets. Okay, so the first step is going to be distinguishing some of the sets, of the measurable sets, and then the second step will be to define a measure on them. So that's the first unit here, measurable spaces. Okay, so let's get right into it. So say you have a set, any set, it should be non-empty, okay? But X is a set, that's maybe like the real line or something like that. So a set A, which is a subset of all possible sets of A, for example, if X was the real line, it's some subsets of the real line, maybe the open intervals or some points or whatever. So a subset of the power set of X, and it's just a bunch of subsets of X, is called a sigma algebra. Sigma is just part of the name. There is no sigma. It's not a parameter. It's just one of the characters in the name. A sigma algebra, if, well, first of all, X itself is in the set. Okay? Secondly, whenever a set A is in the set Mafkal A, this school A, then also its complement with respect to X is in the set. That in particular means that the empty set is in this curly A because X is in curly A by the first assumption or axiom. So that item is called naturally closed under complement with respect to X. And the last thing we want is that if you have any finite or countably many sets in curly A, AIs, could be infinite but only countably many, then their union also lies in the set. Okay, that's called closed under finite or countable unions. And an element in this curly A set is called a measurable or just measurable or a measurable set. So we think of this curly A as those subsets of X that we want to measure. Okay, these are the measurable sets. So you want to be able to measure the entire set X. You want to be able to say that if you can measure a set, you can measure its complement. These are very natural axioms. And you want to be able to say that if you know that some finite number of sets are measurable, then also their union is. And that should hold also for countably many elements in the union, not just finitely many. And the picture here, that will allow us kind of to kind of do things that resemble integrals. So, for example, if you have, this is just a like a figure. Say you have this set. This is this set here, and you can kind of describe it as the union of finite or countably many sets that are measurable. Then you want that thing also to be measurable, right? So you want to extend things countably many ahead. Okay, so X, the underlying set, together with the measurable sets that you chose, is called a measurable space. So it's not a measure space. There is no measure yet, but it's a measurable space. It's a space of things you can measure when at some point someone will give you a measure. Now the point is, you can say, well, before talking about the examples, why don't you just define a measure on all of P of X and that's it? Well, the thing is that, and that was kind of to my understanding, I wasn't there, kind of the breakthrough in this line of works is that you can't, if you are going to insist on being able to measure everything, then your measure is not going to be very interesting, or some very interesting measures cannot do that. Some measures can, but some cannot do that. So typically we cannot assign the measure to any set. So the first thing we need to do is to kind of distinguish the sets we want to measure. These are the measurable sets that we just gave the kind of formal definition for them, in the axiomatic sense. And only then you are in a position to start talking about a measure. Okay? Okay, I hope that's clear. So examples would be the kind of two very non-interesting examples, but nonetheless, so for any x, if you take the set curly A to be phi and x, you know, that's by definition that's a measurable space. It's closed under union, under complement, and so forth. But it's not really interesting because you can only measure two things. And the second thing is that the kind of the other extreme example is that where you insist that you of measuring everything. So you take curly A to be P of X. And that's not going to be useful. It's definitely interesting. I mean, if you could, the more sets you will be able to measure, the better. But that's going to be an overkill. You won't be able to put nice measures on this set in general. Okay. Now, sometimes we are going to have a set M, a subset of the sets that we care about, and we want to have a measurable space that contains M. So of course, P of X contains M, but we want to have a measurable space that contains this set. We really want to measure those sets. We know the identity of those sets, maybe like open intervals or something in the reals. But it could be that by its definition, it's not a measurable space. Maybe it's not closed under complements or you know a union of countably many sets and so forth. So what we would like to do is to say, well, you know, I'm interested in the sorry, one second. So I should have said sigma algebra. I'm interested in the sigma algebra, the smallest one that contains M. Namely, I want to measure the sets in M, but I want my sets to be a sigma algebra, so I want to consider the smallest sigma algebra that contains M. So the way to do it is, one way of doing that is doing from the kind of outer definition. So we're going to define sigma of M to be the intersection. I'm right here, the intersection of all sigma algebras that contains M. That contain M. Okay, that's called the generating. M is called the generating set, and yeah, and that's that. So when I say smallest, you see, I mean with respect to inclusion, because I'm taking the intersection of all possible sigma algebras that contains M. Note that this intersection is not like trivial. Like P of X is one of the participants in this intersection. And also note that's actually something you kind of need to think for a second. The intersection of any number, not necessarily countably many, sigma algebras is also a sigma algebra. Okay. So this definition makes sense. Sigma of M is indeed the sigma algebra generated by M. So as an example, if you take X to be the real numbers, then you can consider the Borel sigma algebra. So what's the Borel sigma algebra? So this is the sigma algebra that is generated, as I actually hinted at before, by all possible open sets, open intervals, like finite open intervals. Okay, from A to B for any A smaller than B. So note that in this sigma algebra you also have points, because and also maybe a more interesting example is actually this one. Points, and you have closed intervals, because you can take the union of countably many you know, some stuff like that. Okay, so you can take the intersection of those, and because you're closed under unions, countably many unions and you close down the complement, you also close under this, and that gives you this closed interval, and therefore you can also have points and so forth, and you can also have the whole, you can also have these things, right? Open intervals that are infinite of one or the other side and so forth, as the union of countably many of the finite intervals, finite open intervals, say. Okay, so again, so when you have a set that you want, set of things you want to measure, you can define the sigma algebra, the smallest sigma algebra that contains M. It exists. You need to verify that intersections and so forth preserve sigma algebra-ness, but they do, but it does. And for the particular case of X in the real numbers, the Borel sigma algebra is exactly the sigma algebra that is generated by all finite open intervals. As a remark, I can say that, maybe I should say it, but maybe I shouldn't say that the Borel sigma algebra is actually with respect to any topological space. If you have a basis for a topological space, then sometimes it's useful to consider the sigma algebra generated by the basis. Okay, but never mind.